at this, I made some corrections. One correction is I mistakenly stated that this was steady state. It was not. The other thing I did that was a mistake was I said that I could treat it as a 2D model. The 1D model is a better, more accurate way, so that's what I'm going to stick with. So first what I did was I found the mass diffusion by multiplying the diffusion coefficient, surface area, difference in concentrations over the length of the diffusion media. And then I found the volume, and then you can find the time by inverting it. So the concentration at what we're looking for, the volume over the mass diffusion rate, and there we have it. For the second part, we find the Rayleigh number, then we find the Nusselt number, then we find the H. We assumed it was a vertical plate. It's a vertical cylinder, but vertical plate model. Q is going to have the H times AS times difference in temperatures. Then we find the T through MCP delta T. That'll give us our change in temperature. As you can see, it's quite small. What you would expect, your T doesn't go cold 2 minutes after setting it up. And then we find the mass diffusion through the sphere. Similarly to this, we're going to change the surface area and make it spherical, and that will give us this time limit. So we're looking at problem 3 here. Here's the properties that we have. For the first part, the Q radiation, I did this kind of out of order, is E sigma surface area times the temperatures to the fourth minus the T infinity to the fourth. What you're going to do after that is you're going to find the velocity. That'll find you your Reynolds number. It'll help you determine how to find the Nusselt number and whether it's turbulent or laminar. So you find the Nusselt number, that'll find you the H value. You can use the H value, rearrange the balance, and that'll give you your final temperature. And then for the last part, because we have a high CP value, because it's phase change, so CP is assumed to be infinity, that'll give us our C min as the cold. We use the equation C equals 0, so we find this equation, and then we get our final answer. So for the first part of the problem, I had the cube. I found the BO number, used the lump analysis. It was under the threshold. I found theta, and then I found the B value using the constants given. I rearranged the equation to find the time. For the second part, I found the properties that I need. I used the nucleate boiling, multiplied all of this together, and I found the cube boil by multiplying by the surface area, which is 5 faces of the cube. And then the last part, for the mass being evaporated, I divide that by the heat of vaporization. So for the final problem, I set the boundary conditions, set the initial conditions, and I wrote down alpha here for you guys so that you could see it. So for this one, I used explicit Euler with finite differencings. I did the 2-dimensional matrix. This is the equation that I got to set up for that, and I'm about to show you the code I built in Python. So this is the code that I ended up building. It uses the explicit Euler method. I went through, I plugged it in. I set up a matrix, which later you end up with a block matrix. I used the method then to create this graph, which will show you the temperature. This is the plot of the graph. As you can see, it dips. I know the graph can be kind of hard to see, so I will show you the table values as well, and you'll see what those are. Okay, as you can see here, here's the matrix I have. The The values are very large towards the outside, like 400s. Towards the inside, you're getting more towards 76. And that is how you program this. So for this last problem, we had a separation problem. We were using a membrane to separate. And for the mass transfer, we needed to find the pressure required up top to achieve 97% of filtration of the nitrogen from the methane. So this is our formula. You're going to have your area of your membrane, which was given to us, equals the flow of the nitrogen, in this case, in the permeate, over the partial pressure in the nitrogen permeate times the driving force. The driving force is down here. This is what we're going to use to find the pressure required up top. So we go through all of this. We're going to find the partial pressure of the nitrogen. I used the solver method to find this. So it ended up getting me 623 kilopascals, which is much higher than expected compared to the other 100 kilopascals in the sweep in the permeate.